Hello, in this video we'll be looking at charging a capacitor, and the equation and the graph. So let's draw a simple circuit to begin with. Let's say we have a 3-volt battery. Like that, so it's 3 volts. And we'll draw it in the typical circuit where we have a capacitor, we have a switch like that, and in parallel with the capacitor we have a resistor. So we'll label that C for capacitance, R for resistance. Now what's going to happen is that when we close the switch, the capacitor is going to charge up to 3 volts, and we could have a voltmeter across there to record that. It's going to charge the capacitor, and then we open the switch, the capacitor will discharge across the resistor. And what we'll find is that now the initial voltage V0 is going to be 3 volts. And if we were to plot voltage against time, we're going to time this. So we're going to see how the voltage changes with time. So we're going to have a clock here. This is a classic example. We're going to time this, and if we're against t in seconds and voltage in volts, you'll find it starts off at V0, which is 3 volts, and it'll fall exponentially off like that. Now, we'll also find that after a certain period of time, call that CR. So in fact, the capacitance in faradays times resistance in ohms, CR, actually gives you time. Okay, so you've got this called tau equals CR. This is known as the time constant. And the time constant, CR, is for after a certain period of time, which is a time constant, the original voltage, the final voltage, we have voltage, will be equal to 0.37 times the initial voltage. There. So that point there is in fact 0.37 V0. So therefore we will know just by multiplying the capacitance times resistance how long it will discharge to 0.37 times the initial voltage. Okay, and now the equation represented by this curve, the exponential equation, is that the voltage, the current voltage, is equal to the initial voltage V0 multiplied by e to the power of minus the time divided by the time constant CR. And what we find is that from this equation here, this exponential equation that describes the path of this discharge curve, and from here we can get this result there. We do that by substituting time into CR. So what we can do is, I'm going to rub this off now. I don't need it for now. We'll draw it back on again if we need to. We could say that if the time is equal to CR, then V equals V0 e to the minus CR over CR, which equals V0 e to the minus 1. And e to the minus 1 is e simply numbers, and e is, I think, 2.718. Something like that. We're going to check that. But therefore, and 1 over that is about 0.371. So V equals 0.371 times V0. So if T equals CR, that's the case. And that's how we get this relationship. And this is the time constant. Now, we've looked at this as discharging through voltage. We've also got charge, and we've also got current. So the graph for charge looks exactly the same as it does for voltage. So for charge, we've got our exponential, and that's Q naught, Q, and that's against time in seconds, and charge is in coulombs. And for current discharging, well, the title says charging capacitor. It's meant to be discharging a capacitor. Okay, that's what we're doing. We're discharging curves. We'll look at charging curves later on. And for current, it follows the same path, falls down like that, where that is I naught, this is the current, and this is the time in seconds. And they both follow the same pattern of formula. So this would be Q equals Q naught e to the minus t over CR, and this would be current equals the initial current times e to the minus t over CR. So these are our discharging curves. Now we'll briefly look at the charging curves, which are very, very similar. Now, if we were to charge, so this will now we can change to charging capacitor. So charging capacitor, we can have here's our 3-volt battery if you like. We have a capacitor and a resistor R and possibly a switch there. Okay, so this time how we're going to plot it, we're going to start off with an uncharged capacitor, and we're going to plot, let's put a voltmeter across the capacitor. Okay, so we're going to plot what happens when you're charging up. Now the charging curve, it will rise to something called a V naught, in this case 3 volts is the V naught, and it will rise from naught in time, seconds, like that. And as it'll theoretically it'll never reach 3 volts, but it will. And this time we have a time constant, tau equals a time constant CR. But for charging, we'll find, so when time is equal to CR, what we find is that the V is equal to 0.63 times V naught. And this is because our equation for charging is in fact V equals V naught minus V naught e to the minus t over CR. So when we substitute the idea of CR into t, we get, after time CR, we will get 0.63 of our final voltage. This is charging capacitor. Now it's exactly the same format, the look for the charge in capacitor. Okay, so for charge, we would get, so this is Q naught. So charging capacitor, with its capacitance, that would be charging capacitance. Time in seconds would look like that. However, the current for charging looks exactly the same as it does for discharging. The current always starts off at its maximum and then falls exponentially away by I equals I naught e to the minus t over CR.